Alright, let's start with something simple. When we talk about assembly line balancing, what we are really talking about is how we distribute work across all the stations in a production line so that everything moves smoothly. No one's overloaded, no one's waiting around. That's it. The idea is to keep the workload even, minimize wasted time, and make the whole line as efficient as possible. Think of it this way. Every workstation along a line has its own tasks to complete. If one person is too busy while another finishes early and waits, the line slows down. Balancing helps us fix that. So the flow of work keeps moving at the right place and production targets are met without chaos. Now, the main goal here, or what we call the core objective, is this: distribute all those work elements across stations in a way that uses as few stations as possible while still maintaining the output rate we want and following the order of tasks. So it's a mix of efficiency and logic. We want speed, but we also have to respect how things depend on each other. And let's talk about why this even matters. In real production settings, even a small imbalance, say one workstation taking a few seconds longer than the rest, can cause big issues when you multiply that across hundreds or thousands of products. It's like traffic, one slow car can back up an entire highway. And if a line is not balanced, you get bottlenecks. Workers might end up tired because they are doing too much while others sit idle. Inventory starts splitting up between stations, and throughput, the total number of finished units, goes down. And overall, the factory just runs less efficiently. But when the line is properly balanced, everything flows. Resources are used effectively, people work steadily, and products move along without interruption. Okay, now take a look at the key benefits here. When we balance a line correctly, a few things happen. At first, we get higher throughput, meaning we produce more units in less time. That's because we have eliminated bottlenecks. Then we cut costs, fewer idle times, and less wasted labor. Next, the workflow becomes smoother with less inventory building up between stations. And finally, we keep the workload fair, which helps prevent fatigue and keeps quality consistent across the board. Let's continue. On the screen you can see two lines, one unbalanced and one balanced. So let's look at the difference. On the left side, the unbalanced line is inefficient. You will notice some stations are overworked. For example, WS2 and WS4, workstations, take much longer. That means the others have to wait. And here the cycle time, that's the longest workstation time, is what is that? Here 70 seconds. The total efficiency is about 68%. Idle time adds up to 110 seconds, and output per day is around, what is that, 411 units. Now compare that to the balanced line on the right. All stations are close in timing, around 61 to 64 seconds each. The cycle time drops to 65 seconds. Efficiency jumps to here 94%. Idle time shrinks to just 15 seconds. And output increases to about, look at this, 443 units per day. So the takeaway: balancing doesn't just make things look better on paper. It has a clear, measurable effect on how much you produce and how smoothly it all runs. And okay, next, stop. Before we go deeper, we need to make sure we understand a few key terms, and these are the building blocks of everything in assembly line balancing. First, cycle time. This is the maximum time a product can spend at each workstation if we want to keep up with production's targets. It basically sets the rhythm of the line. If one station exceeds it, we will fall behind. Then there's a takt time. Here, pronounced takt, like a musical beat. This one tells us the pace we need to maintain to meet customer demand. And it's calculated by dividing the available production time by the number of units customers need. So if customers want more, takt time goes down and we need to move faster. Okay, next is station time. That's just how long it takes to complete all the tasks at a particular workstation. To keep things smooth, this can't exceed the cycle time. If it does, we get bottlenecks. Then we have the idle time, the difference between cycle time and the actual working time at a station. Idle time means wasted capacity. It's a hint that we could do better. Balance delay here. This shows the percentage of the total time that's idle. A lower balance delays means our line is better balanced. Okay, and line efficiency, that's the ratio of productive time to total available time. And let's connect all these terms. You can see on the screen here a simple bar showing total production time and idle time. Here, total available production time is, let me show you, where is here, 480 minutes, and total task time, that's the actual working time, is 288 minutes. That means 142 minutes are idle. To measure how efficient line is, we use this formula. Efficiency equals total task time divided by all multiplied 100%. So here that's 288 divided by, and here 6 times 80 times 100%, which gives us 60% efficiency. Then balance delay is simply what's left, 100% minus efficiency, so here 40%. The goal is to keep that idle part as small as possible, meaning the productive portion here, green bar, stays large. Okay, and inside you can read. Okay, and let's continue here the math. We move into mathematical side of balancing, and we will start with the formula for cycle time. Look at this. Cycle time, written as C, is equal to available time per day divided by required output per day. And cycle time is measured in seconds per unit. Okay. When we calculate it, we consider total working hours in a shift, subtracting breaks or maintenance stops. The required output is the total number of units we need to make each day based on customer demand, sometimes with a small safety margin added. Okay, and look at this. We find the theoretical minimum number of workstations shown with the formula here, and sub mean equals the sum of all task times divided by cycle time rounded up. And here the sum of T sub I means we are adding all the task times together. Dividing by C, it is the cycle time, tells us how many full workstations we would need to handle that workload if everything were perfectly balanced. The rounding up part, that's because you can't have a workstation. Line efficiency, here we calculate the formula is here efficiency equals the sum of task times divided by times 100%. A higher efficiency value means a better balance, more of your available time is being used productively. Balance delay, here It is simply the percentage of time that's wasted. In other words, when stations are idle, and the formula is here, balance delay equals 1 minus efficiency times 100%. A lower balance delay means a smoother, better performing line. The ideal goal is to minimize this delay while still meeting your production rate. And smoothness index here shown as Si equals the square root of the sum of that St max minus Sti squared. And here St max is the maximum station time, usually equal to cycle time, and Sti is the time at each individual station. The smaller this number is, the smoother your workload distribution. So if every station's time is close to the same, your smoothness index will be low, and that's a good thing. And practical example, let's look at this. Here, available time, required output, cycle time, and total tasks. And here our scenario, and that's our calculation. And look at this number of stations is 3 now, but let's change. Line efficiency is here, balance delay is here, and change again. Line efficiency here 50, and here. Okay, that part is done. And line balancing techniques. Okay, you have seen the idea on the metrics. Now it's time to see the methods we can use to assign tasks to different workstations. And there are a few common techniques used for line balancing. Each one works a bit differently depending on how complex the process is and what kind of constraints we have. Let's start with one of the most straightforward methods, the longest task time method. That's here. What is that? Alright, here's the basic logic. We start by dividing priority into tasks that take the longest time to complete. The idea is that longer tasks are harder to fit into the process later, so we handle them first. By placing them earlier, we leave more flexibility for the shorter ones. So how do we actually apply this method? First, we rank all the tasks by duration, from the longest to the shortest. We also take note of any precedence relationships, meaning which tasks depend on others before they can start. Next, we assign the longest available task to the first workstation, but we make sure it fits within the remaining cycle time and follows those precedence rules. Then we keep filling that workstation until we can't add any more tasks without exceeding the cycle time limit. Once that workstation is full, we move on to the next one and repeat the process until every task is assigned somewhere. And if you look at the diagram here, you can see these visually. The tasks are ranked by duration. Task A takes here, look at this, 35 seconds. Task B takes 28 seconds. And task C is here, 25, and so on. When we start assigning, station 1 ends up with tasks A and B, totaling 63 seconds, which is about 90% of the allowed cycle time. Station 2 takes tasks C, D, and E, which together make 67 seconds, giving us a 96% load. Finally, station 3 handles tasks F, G, and H, totaling 45 seconds, or about 64%. And you can see how each station stays within the 70-second cycle time limit, which keeps the line balanced and efficient. Okay. Now sometimes the process is more complex and we can't just go by duration alone. That's when the ranked positional weight method comes useful. So here, instead of just looking at how long each task takes, we look at how important it is in the overall sequence. We assign what's called a positional weight to each task. This weight equals to tasks on time plus the total time of all the tasks that depend on it. The formula looks like this. You can see positional weight sub I equals task time sub I plus the sum of all successor task times. And this helps us identify which tasks sit on the most critical paths through the process. Tasks with higher positional weights get assigned first because they have a bigger impact on the workflow. So step 1, we calculate each task's positional weight by adding up its duration and the times of everything that follows it. Step 2, we rank tasks from the highest to lowest positional weight. Step 3, we assign tasks in that order, making sure we still respect precedence rules. Step 4, here we fill each workstation to capacity before moving on to the next, keeping idle time as low as possible. And okay, Kilbridge and Western method. This one helps you when you have complex network of tasks with many dependencies. And what it does is group tasks into columns based on their presence relationships, and then assigns entire columns or partial columns to different workstations. It's a more structured way to handle complicated presence diagrams. And if you look at the comparison chart here, you can see how these methods perform. The longest task method gives a line efficiency of 82% using 6 stations and taking about 5 minutes to set up. And the ranked positional weight method performs better. It hits 88% efficiency, needs only 5 stations, and takes around 15 minutes for setup. And the Kilbridge and Western method lands somewhere in between at 85% efficiency with 6 stations, about 20 minutes of setup. So depending on your production environment and how complex your process is, you choose the one that balances precision and effort best. Okay. Now let's move on to something equally important, understanding how tasks depend on each other. We call this visualizing task dependencies. And the main tool for that is the precedence diagram. Alright, this kind of diagram helps us figure out which tasks must be completed before others can start. It is the foundation for making any line balancing decision. So how do we read one of these diagrams? And look at this. Each circle or node represents a task. Inside that circle, you will see how long the task takes. The arrows show which tasks must happen before others. If a task doesn't have any arrows coming into it, it can start right away. But if it has multiple arrows pointing toward it, that means all of those previous tasks need to be done first. And if you look at the example diagram here, you'll notice tasks like A, B, C branching out from the start. Task A takes 20 seconds, task B takes 25, and task C takes 15. From there, each of those leads to other tasks like D, E, F, which eventually merge into G, H, and I before reaching the end. And the arrows show the logical sequence from start to finish. Alright, and now there is one special part of this diagram we need to focus on, and the critical path. Look at this. This path shows the longest sequence of dependent tasks. Why does that matter? Because the total time along this path sets the minimum possible cycle time for the entire process. And if any task along this path is delayed, and the whole production line slows down. And okay, here critical path is here. Look at this. Critical path is highlighted in red. You can see it goes through tasks B, E, G, and I. And if you add those up, it gives a total of 135 seconds. That's the time that defines how quickly the line can operate at best. The other tasks, which are shown in blue, are non-critical. Delays in those won't immediately stop the line unless they eventually affect the critical tasks. And look at this interactive precedence work. Let's think about what happens if we change some task durations. And look at this task duration. Task 3 duration, 25, task 5 duration, and 30, and let's change. And here, for example, here and here, and look at this like that. And okay, I hope that's done. And let's continue. Okay, step by step parts. We will talk about this. And when we talk about line balancing, we are really talking about finding the most efficient way to distribute tasks across workstations so that production runs smoothly without bottlenecks or wasted time. So let's break this process down clearly. We start by defining production requirements, of course. Here we look at how many units we need to produce in a given day, how much available production time we have, and what quality standards must be met. Once we know this, we calculate the target cycle time. That's the maximum time each workstation should take to complete its tasks to meet daily demand. For example, if we need, let's say, 500 units a day, and we have let's say 25,000 seconds of available production time, our cycle time would be 50 seconds per unit. That's just dividing total time by required output. And okay, after we have set that goal, we move to breaking down the assembly process. Basically, we list every single task that goes into producing one unit, and each task needs a standard time value measured through time studies or historical data, and this step ensures we know how long each operation takes before we even think about balancing. Okay, next comes mapping precedence relationships, and this means identifying which tasks depend on others. Some tasks can't start until certain ones are finished. To visualize this, we create a precedence diagram. What must come first, what follows, and which can happen in parallel. And this diagram becomes the backbone for our balancing later. And once we have that map, we calculate theoretical minimum number of workstations using the formula n minimum equals the sum of all task times divided by cycle time. This gives us the absolute lowest number of stations possible if everything were perfectly balanced, which rarely happens in real life, but it's a good benchmark. After that, we apply a balancing method, and this could be the longest task time, ranked positional weight, or another heuristic approach. The idea is to assign tasks to stations while respecting two things: the cycle time and task order. We keep assigning tasks to each station until we reach the cycle time limit, then move to the next one. Then we calculate performance metrics, and here we measure things like line efficiency, balance delay, and smoothness index. Line efficiency tells us how much of our total available time is actually being used productively. Balance delay shows how much time is being wasted because of uneven distribution, and smoothness index gives us a sense of how evenly tasks are spread across stations. And here, refine and optimize. Once you see your first balance, you almost always find places to improve. Maybe one station is overloaded while another has slack, so you can reassign tasks, combine small ones, or redesign the station layout to achieve a smoother balance. That's where most of the fine-tuning happens. And validate your works and implement. And okay, we have an animation here. Look at this. Station 1, Station 2, and Station 3. A, B, C, D, and E, F. That was speed. You can see clearly now. Okay. Alright. Let's talk about practical implementation, because theory and real life are not always the same, right? In real factories, manufacturing, we have to deal with all sorts of variables that complicate things. Human skills, emission limits, quality checks, and even space constraints. Okay, let's go through some common challenges. What are they? The first one is variable task times. Let me show you here. Sometimes a task doesn't always take the same amount of time. Maybe the material varies or the operator works at a different pace, and this can create uncertainty and bottlenecks. The solution is to use statistical analysis. We set conservative time estimates and include safety margins so that variations don't mess up the whole balance. The second challenge is worker skill differences. Not everyone works at the same speed or with the same accuracy. Some operators might need more time. To handle this, companies often use cross-training programs, allowing workers to be flexible and to switch roles when needed. And that keeps things moving, even if one station slows down. And we have got equipment limitations. Certain tasks might need special tools or machines. In that case, we group similar equipment together or design mobile tool stations so that production doesn't get stuck waiting for a specific machine. Then there is quality control points. Inspections sometimes don't fit neatly into the cycle time, which can throw off the rhythm. A good approach here is to integrate quality checks into normal tasks whenever possible, or dedicate specific quality stations for them. And here, physical constraints. Sometimes you just don't have enough floor space for ideal layouts. So you might redesign your line, maybe use U-shaped cells or vertical arrangements to save space and keep the workflow tight. And we have case study here. And electronics assembly optimization. So before optimization, there were 8 workstations. Efficiency was at 68%. Throughput was 320 units per day, and the balance delay was here 32%. Labor costs were around, what is that? 147,000 per year, of course dollar, and you can see that same, here you can see that some stations had much higher loads, like WS2 and WS6, while others had idle time. That's a sign of imbalance. And after rebalancing, the company reduced the number of workstations to 6. Efficiency jumped to year 86%. Throughput increased to 440 units per day, and balance delay dropped to 14%. That's a huge improvement. Fewer stations, less delay, more output, and all they did was redistribute tasks more evenly. And here our cards, and let's continue. Alright, here, let's stop. Advanced balancing topics. These are techniques used when production environments get more complex, like when you are building multiple product variants or handling constant changes. And the first one is mixed model assembly lines. In many modern factories, we don't build just one product, of course, we build different versions of the same line. For example, Model A, Model B, and Model C might all share some tasks, but have different times for others. Mixed model balancing makes sure all these variations fit within the same cycle time, so production keeps flowing smoothly. And take a look at this example. Each model has different task durations at each workstation. For instance, Model A might take 45 seconds at workstation 1, while Model B takes 38 and Model C takes 50. The idea is to average them out, so the workload is balanced across all models. The target cycle time here is 52 seconds, so every workstation should ideally stay below that average. And next we have got dynamic rebalancing. In real factories, things change all the time. Demand goes up or down, new products are introduced, or process improvements happen. And instead of redesigning the entire line each time, dynamic rebalancing lets us adapt on the fly. Okay, and there are a few strategies to do this. One is having a flexible workforce. Operators trained to handle multiple stations so they can quickly switch roles when needed. Another is using digital work instructions, electronic displays that update automatically when assignments change. Then we have modular stations, meaning workstations that can be reconfigured or even relocated easily. And finally, real-time monitoring using sensors or software to track line performance and spot imbalances as soon as they occur. Let's touch on two-sided assembly lines. These are often used for large products like cars or appliances, where operators can work on both sides of the line at once. This approach makes better use of space and can shorten line lengths quite a bit. For example, a traditional single-sided line might be 42 meters long, but a two-sided line for the same product could be just 24 meters. And that's about a 43% space saving. Okay, and here stochastic task times. In reality, task times are not fixed, they vary. So stochastic models help us handle that uncertainty using probability distributions. These models don't assume that every worker or machine performs at the exact same rate every time. Instead, they account for variability when balancing, and the formula we use for expected station time with variability looks like this. What is that? E of S sub I equals the sum of mu sub j plus z times the square root of the sum of sigma sub j squared. And here Here, this stands for the mean time for each task J. This. And here, this is the standard deviation for that task. And here, safety factor that corresponds to our desired confidence level, basically how much variation we want to cover. This formula helps plan and helps us plan more realistic station times when variability is present. And overall, these advanced topics all help make modern production systems more flexible and reliable. And that's okay. Let's continue and let's see what is next. Measuring line performance, and let's talk about this. Okay. Continuous monitoring of key performance indicators ensures that line runs at peak efficiency and helps us find opportunities for further improvement. And we start with the primary performance indicators. The first one, overall equipment effectiveness, sits at 85%. Just example, that tells us that most of our available production time is being used effectively, but there is still room to tighten up small inefficiencies. Next, the first pass yield is an excellent 97.2%, meaning almost every unit passes inspection the first time without rework, which reflects a strong, stable process. Then we see actual versus target output, which is at 102%. That's a great sign. We are slightly ahead of plan. Finally, the average idle time is 4.2 seconds per station, showing that while the line is well balanced, there is still a little bit of unused capacity waiting to be optimized. Looking below, we have the workstation performance analysis. Each bar represents a workstation from WS1 to WS6, showing how much of its cycle time is spent performing actual work versus sitting idle. And the green portion is active task time, and the small beige section on top represents idle time. You can see the times range between 58 and 63 seconds. A tightly consistent spread. That means tasks are distributed evenly across the line and no single workstation is being overloaded or underused. This consistency is exactly what we want from a balanced process. Now, even in a balanced system, there is always one limiting factor. What is that? Bottleneck. The bottleneck impact simulator here shows us how one station can affect the entire line. And here station 3 has a task time of 60 seconds and it's operating at full capacity. Okay, 100% utilization. Because of that, the line throughput caps at 480 units per day, while the other stations average about, what is that, 8 seconds of idle time. And this illustrates a key principle: the whole line can only move as fast as its slowest station. Think like a train. And that's why bottleneck management is critical. Focusing improvement efforts on that one limiting point gives the biggest gains. Even a small reduction in task time at the bottleneck immediately increases total throughput, while similar changes at non-bottleneck stations have almost no effect. So in short, by tracking these performance indicators continuously and by understanding where the constraints are, we keep the line running at maximum efficiency and make star targeted improvements. Okay, here, other things. And I think we will look at final part. Yes. Now that we have covered how to measure performance, We will move to implementation best practice, the part where careful planning turns design into successful reality. And successful line balancing doesn't just depend on numbers or layouts. It depends on data accuracy, teamwork, ergonomics, and discipline and execution. The pre-implementation checklist outlines the steps to make that happen. First, we collect accurate data. That means performing detailed time studies on every task under realistic conditions and documenting all the details from material handling to quality checks. Without that solid foundation, every decision that follows becomes guesswork. Next, we engage the team. Operators who work on the line every day often notice constraints that are not visible in the data. Their feedback is important to making a design that works in real life. And here we design ergonomically. Workstations must support safe and comfortable work. Poor ergonomics lead to fatigue, quality issues, and slower task times over the long term. We also plan for materials. Materials need to be presented efficiently to minimize reaching, searching, or waiting. Smooth flow of materials translates directly to smooth production. We built in flexibility here. Stations should be able to handle changes, whether that's reassigning tasks or adjusting for new product models. Once that's in place, we pilot test the line. A controlled trial lets us identify and fix problems before the full rollout. Then we train truly here. Every operator should be confident in new task assignments, quality standards, and troubleshooting routines. And we monitor closely. During the early phase of implementation, tracking metrics frequently allows us to react quickly and fine-tune performance before problems spread. Of course, even with the best practices, there are pitfalls to avoid. What are they? Ignoring task precedence leads to impossible work sequences and quality problems, and overlooking reliability can cause unexpected bottlenecks. Neglecting the ergonomics leads to fatigue and slower sustained performance, and insufficient training causes frustration or errors. And these mistakes are common, but all of them can be prevented with good planning and discipline. Yes, and finally, we see the implementation timeline, just an example, which spans 6 weeks from start to finish. Week 0 begins with data collection, establishing the baseline, and by week 1, the analysis and design are underway. Week 2 sees design approval. Week 3 is for pilot testing. Week 4 focuses on training, and by week 5 we are ready for full implementation and go live. The final week here, week 6, is for monitoring and adjustment, making sure the target performance is met and the line runs as intended. And okay, thank you for listening.